Thank you. So first of all, thanks to the organizers for this invitation. I really appreciate to be in this very nice and stimulating environment, and I've enjoyed the talks so far this week. So I'll be talking about critical phenomena with interacting photons, and hopefully the title is a bit of provoking, right? Because many of you know photons in free space don't interact, and then you can wonder how they undergo phase transitions. So I'll be talking about this in further detail. So a bit of the motivation comes from way back in medieval times, where people were building analog simulators for different purposes. And the idea is that you construct a physical system that has convenient length and time scales, and it's easy to probe. And you can use it, for instance, to learn or predict something about the original system. For instance, this is orreries that were built as a means to learn about astronomical events and keeping track of time and so on. I think more recently this has also been studying phase transitions in the early universe or condensed matter systems. It's another topic that I'll come to later. A second reason to build an analog simulator could be to solve hard problems. And one of these problems I'll be talking towards the end is finding, for instance, the ground state energy of a spin model. So we in photonics derived a lot of inspiration from what happened in the last decade in ultra-cold atoms, where people will be building quantum simulators made of atoms in optical lattices. And a lot of the hype came from studying quantum phase transitions at 0 temperature. And in the last decade or so, people have been basically reversing the role of light and matter and studying photonic simulators, where now you can have photon hopping, interaction on site via Kerr-type nonlinearity. So this is pretty much a Bose-Hubbard model. But now you have coherent driving and loss. And so you have a steady state that is a non-equilibrium that arises from the balance between driving and dissipation. There are several experimental platforms where this has been realized. In the groups in Stanford and in Japan, there's been work on optical parametric oscillators simulating Ising models. The group of Jeremy Bomberg was also studying different type of ferromagnetic systems with polaritons. Jan Klaers and Martin White studying photon BEC. Recently they started to do lattices as well. And in superconducting circuits, there are several groups as well that are looking at strongly correlated systems in 1 and 2 dimensions. So I'll be talking about the system that we work with, which is cavity polaritons. I'll give you an introduction to the system. You heard about it before, so I'll go very quickly. Then I'll do most of the talk on the phenomenon of dynamic hysteresis and dissipative phase transitions. And towards the end, I'll talk about what we started building in my group since about 10 months ago, where I started in Amolf, and the perspectives we have for building a photonic Ising simulator. So cavity polaritons, they arise from the strong coupling between a photon and an exciton. The photon has a parabolic dispersion at small momentum, as you have seen before. The exciton is pretty much flat. And from the strong coupling, you get an avoided crossing between the upper and the lower polaritons. In this case, you're seeing the photoluminescence intensity as a function of energy versus K parallel. So the polariton is part light, part matter. From the light, we get a tunable effective mass. We get the ability to probe and confine the system with light. And the very easy way to understand this is, if you recall back from introductory quantum mechanics, when you have a particle in a box, the potential energy will go as 1 over L squared. So basically, if you take this 2D cavity and you confine by making a pillar, then you create a potential for polaritons, and then the lower polariton band gets discretized. It's no longer a band, but continuous. So it becomes discrete states. And the energy between the separation between the states goes as 1 over L squared. Now, the most interesting part of polaritons is that from the exciton part, we get effective interactions. So I want to briefly illustrate the consequences of this interaction, taking a very simple model, which is a kind of nonlinear Schrodinger equation in 0 dimensions, right? And where we add now loss and driving. So for weak driving, I plot the density, which is alpha squared in units of the interaction constant divided by the loss rate, as a function of the detuning between the driving frequency and the resonance frequency normalized to gamma. So for weak driving, you get a Lorentzian resonance. For strong driving, interactions become significant, and you get a blue shift, and you see bistability. So there are 2 stable steady states at a single driving condition. If you were to scan the frequency at constant driving amplitude, you see hysteresis coming this way and returning this way. Conversely, if you fix the frequency and you scan the amplitude, you see the characteristic S-curve of bistability. Now, there is a lot of very interesting and fascinating physics emerging from interactions, which I've been studying over a number of years with polaritons. I think the holy grail in the field is to realize the Polariton blockade regime, which people have been trying for 20 years, and so far nobody has succeeded. And the physics is simple. It's just that when the interaction constant is comparable or greater than the line width, the presence of a single photon in the cavity blocks the entrance of a second one. So this automatically converts coherent light, which is the most classical of all quantum states, into a single photon source. Now at the mean field level, there's a number of other intriguing effects related to the propagation of polaritons in the place. For instance, this works on superfluidity, where people show that above a certain density, polaritons will no longer be reflected by an obstacle, but rather flow across the obstacle without dissipation. Recently, we published a paper where we show how you can control the phase that a photon picks when he hops between one cavity to another by means of photon interactions, and we measure this phase using interferometry. So if you're interested, this is the reference. I'll not be talking about that today. I think another very interesting perspective that I'll come later to the talk is that you can map an array of bistable cavities, just as I described, to an Ising model, where now the two states of the bistability map to the spin up and spin down of the system. Okay, so now I'm going to talk about dynamic hysteresis and a dissipative phase transition in a zero-dimensional system. And there's something very important that I missed in this mean field description that I gave you. And it is the fact that the mean field models neglect quantum fluctuations. So let's describe the system using a master equation formalism. So this is the Hamiltonian, where you have the mode energy, the interaction energy that corresponds to this kernel linearity. You have coherent driving, and we describe the dissipative dynamics with a Lindblad master equation. So this is the conservative part, and these are the Lindblad terms, taking account for loss. Now, to find the steady state of the system, you can write this equation in this very simple form, where you now have d rho dt, rho being the density matrix, is equal L acting on rho, where L is the Liouvillean super operator. It's an operator that acts on an operator to give you another operator. And so you can see from this equation that the steady state corresponds to the zero eigenvalue, right? When d rho dt equals to 0. In particular, the steady state density corresponds to the zero eigenvector. So this problem was solved exactly already in 1990 by Drummond and Walls. And they find something that at first sight is a bit surprising. When they calculate the density as a function of the applied field using the master equation formalism, they get this continuous line here. And you see that there is a unique steady state. When they perform the mean field approximation, and instead of calculating the density in this way, they just take the magnitude square of the coherent field, they recover the mean field bistability. So this is very dramatic difference, right? It's surprising. How can you get such a qualitatively distinct behavior by making just an approximation? So is there something wrong, or how can we explain 40 years of optical bistability? This was the first report of optical bistability experimentally by Gibbs in '76, where they put sodium atoms in a cavity and they just scan the power up and down, and they see this hysteresis characteristic of bistability. Now I also want to point out that bistability is an old story, but if you just look in the last 2 years, the number of citations have very dramatically increased, right? So it seems that there seems to be a kind of comeback of this topic, and I'll try to explain why. So the solution to the apparent paradox was already pointed out by Risken in the 80s and co-workers. And the idea is that you can look at the two mean field steady states like the minima of a double well potential, where now when you include quantum fluctuations, there is a finite probability that the system will stochastically switch between these states. And the probability increases with the strength of the fluctuations, which obviously will depend on this barrier, which depends on the nonlinearity and the detuning and all the system parameters. So this is a calculation I made using a kind of, so neither the mean field equation, but neither the quantum master equation, but using basically a mean field equation plus a stochastic term, which is basically known as truncated Wigner approximation. So this is the usual mean field equation that I show you, now written in the rotating frame, meaning in the frame that is rotating at the driving frequency. And I added this stochastic term, zeta, which has zero mean and is delta correlated. And this corresponds to the quantum noise. Basically, the variance is given by the dissipation, which comes from fluctuation dissipation theorem. And you see that in the phase space, which basically is just the imaginary part of alpha, and this is the real part of alpha, if you evolve this equation, you build a histogram, and then you can get a kind of quasi-probability distribution, which corresponds to the Wigner function. And you see that there is these two peaks, which coincides with these two peaks here of the mean field. So you see this Wigner function is bimodal. Okay, so let's look at the time scale of, I was telling you about a finite probability for switching, so let's look at what is the time scale for this switching. So here I show you a calculation of the tunneling time for bistability as a function of the detuning between the drive frequency and the resonance frequency of the cavity. And I chose 3 values of the nonlinearity that are characteristic of polaritons, all of them in the weakly interacting limit. And you see, notice that this scale is in logarithmic scale, okay? So I want to give you, this is a function of detuning normalized to loss. I want to give you a little bit of an intuition for what this number means. So if this is your nonlinearity, what I'm telling you is that there is a time scale in the problem that for our cavities which have quality factors of order 50,000, there is a time scale in the problem that if you change the driving frequency by 10 picometers, this time scale would go from nanoseconds to seconds. And if you change it by just a few picometers, this time scale will go to the age of the universe. Right? So it's extremely pronounced effect. And interestingly, this becomes stronger the weaker the nonlinearity. So the implication of this time scale is that if you were to scan the driving power across a bistability, the transition from sort of the classical to the quantum prediction would occur when the scanning time is commensurable with the tunneling time. Right? So if you scan fast compared to this time scale, you will see a bistability, but if you scan slow, you will not. So this was further explored in this theoretical paper from the group of Cristiano Ciuti, where they look at the steady state density as a function of the applied intensity for different scanning times. And they quantify the hysteresis area, which is basically the density coming down minus the density going up. When they do mean field theory, they find that the area scales as a power law with an exponent minus 2/3 for any parameters. This is the time scale of the scan in logarithmic scale. Interestingly, when they do it with a quantum model, they find that for fast scans, the two models agree. But as the scan gets slower, there is a transition from one power law to another. The exponent of the first power law of the area is minus b, depends on the system parameters. So if you tune the frequency or the nonlinearity, it will be in general different. But the second power law displays an exponent that is universal. It's minus 1. So this is independent of the system parameters, no matter your nonlinearity, your loss, or detuning.
So wouldn't you expect that the results depend on the absolute size of the cavity, laterally speaking?
Great question. Indeed, the results depend on the size, but I will come back to this point later, because the size will determine the nonlinearity. So I will actually use the size of the cavity to tune the nonlinearity. Now you may wonder, this is an old problem, right? You may wonder, surely somebody must have looked at the hysteresis in dynamic hysteresis in nonlinear resonators. In fact, Jung and Roy did in the 90s. And what they find is that the area of the hysteresis loop scales as 2/3 the power of the switching frequency. So they basically developed and confirmed the mean field prediction, right? So was the quantum theory wrong, or what happened? Now the crux of the matter is that they didn't look at small switching frequencies, which is long scanning times. And so this is the experiment that we redid to find when I was a postdoc in Paris to compare the two predictions. So this is the experiment we built. We have a semiconductor microcavity at 4 Kelvin. We have a single mode laser that we modulate with a waveform generator and sending consecutive ramps of different time duration. And in this way, we vary the time scale of the sweep. We measure the transmission. In this case, this is actually an experimental measurement of the transmitted intensity versus the incident intensity. And when you plot this versus this, you get this hysteresis. And you see there are multiple lines here with just the hysteresis area closes as the sweep becomes slower. Now, our experimental parameters are the nonlinearity, which we tune via the exciton fraction. And actually, it's a very exquisite control because the nonlinearity scales with the square of the exciton fraction. Okay? And so this comes back to the topic of the area. By tuning the area of the cavity, we can choose how exciton or photon-like the polariton is. Of course, we can also change the gamma by either the mirror reflectivity or the material absorption. And the control parameters are the driving frequency and the intensity, which we control with the modulators and a tunable laser. So I want to show you measurements of single-shot hysteresis versus average quantities. So the thin lines in this plot are single shots. I show you transmitted intensity versus power. In this case, when I go up in power, is the black curve. It's coming here. It makes a quick excursion, comes back. There is another jump. It comes back. And there is another jump, and it stays here. When I come back an entirely different way. Yeah, now there is only just one jump. If I repeat this 1,000 times, I get the thick lines. I come up through the black and back through the green. These scans were done in 0.1 milliseconds. If I now change it to 0.4 milliseconds, now you see many more jumps. And so on average, the hysteresis area closes because of the influence of fluctuations. And in the limit of an infinitely slow sweep, you recover the prediction of a unique steady state. These are other measurements of average dynamic hysteresis. I was quite happy when we got these measurements. They look as clean or even cleaner than the calculations. So here is for a large detuning where you see that within the same range of timescales, there is a very small variation of the hysteresis area. But when you change the detuning a little bit, then the hysteresis area closes within this timescale. Obviously, this closes within the resolution limit of the experiment. And in this case, for this detuning, right around here is the tunneling time. So now I present you a plot of the average hysteresis area as a function of this quantity, which is an inverse velocity of the sweep. So if you consider the power as a distance, and then this is the time of the sweep, then this is a kind of inverse velocity. For a large cavity, you see that the hysteresis area changes negligible. In this case, the three cavities are probed at the same laser cavity detuning. Yeah? So mean field prediction would predict, mean field theory would predict exactly the same behavior for the three cavities. So for a large cavity, the area is constant with the inverse velocity. For a medium cavity, you start to see this behavior. And for a small cavity, you see this -1 power law that was predicted. Now, it was quite a challenge to make these calculations for the group of Cristiano in this case. And the reason is the numbers. So the time scale of the sweep is about a millisecond. The resolution that you need to have is a picosecond, better than the Polariton lifetime. Then if you have, in this range of photons, quickly you go to Liouvilleans that are more than 100,000 by 100,000. And then you want to do 1,000 realizations. So already for just one cavity, this is very challenging. And of course, the aim is to go to lattices where this will be completely intractable. And so we tackle this problem in a very different way. That I don't have the time to explain you all the details, but I just want to give you the essence of the model. And the model draws inspiration from a very famous model, which is the Kibble-Surek mechanism, which was introduced in the context of cosmology, and people started to look at it more intensely in condensed matter recently. And the idea is that when a system undergoes a phase transition, there are two timescales that matter. One is the transition rate, so how fast you pull the system across the critical point. And this is the inverse transition rate is this red curve. 0 here is the critical point. And the other timescale that matters is the reaction time. This is basically the tunneling time for us. So in a second order phase transition, the reaction time diverges at the critical point, and this is what leads to the phenomenon of critical slowing down. And you see that there is a region in the vicinity of the critical point where the reaction time is greater than the inverse transition rate, and there is a region outside where it's smaller. In this region, this is an adiabatic stage because basically you're pulling the system and the system can react within the time scale that you're pulling in. In this case, it's a non-adiabatic stage because you're trying to pull the system, but because of the critical slowing down, the system cannot follow. So then the dynamics become adiabatic. And so the insight was that we can get the reaction time from the spectrum of the Liouvillean. Particularly, we showed that in the vicinity of the B stability, I told you before that the zero eigenvalue gives you the steady state, but the lowest non-zero eigenvalue gives you the reaction time. And this one becomes strongly suppressed in the B stability. So we get this one from here. And the insight was that the transition from adiabatic to non-adiabatic dynamics corresponds to the emergence of hysteresis. So we basically quantify this width. So essentially what I'm telling you is that hysteresis is an emergent phenomenon that emerges when you pull a system in a timescale that is shorter compared to the time in which the system can react. So in this way we calculated this non-adiabatic range as a function of this kind of inverse velocity. So I want to stress that we learned something about the dynamics without performing time evolution, right? Just from the spectrum of the Liouvillean and from the known transition rates. And we were able to get a nice qualitative agreement. In this case, we chose the nonlinearities based on another procedure from the experiment that I will not discuss, but if you have questions, I can talk in the end. And so you see as the nonlinearity gets stronger, you see this transition towards the -1 power law predicted by quantum theory. Okay, so after this paper, the group of Cristiano further developed this topic, and they show that in the limit of high density, as you expect, fluctuations become negligible, and there is a first-order phase transition. And you can see this by basically performing the following approximations or limits. If you let the nonlinearity tend to 0, but you let the density tends to infinity, and you keep the product constants such that they're of order gamma, and therefore you have B stability, then the tunneling time diverges. And in these limits, fluctuations are negligible. And so you see that the density becomes, rather than this very slope curve as a function of the applied field, becomes kind of discontinuous, as you expect for a first-order phase transition. So I want to show you another way in which we can actually measure this Liouvillean gap that I've been talking about, so how we can extract this tunneling time for B stability. And it's, in the quantum community, people call this quantum trajectories. Okay, I will just call it a trajectory to not make the quantum claim very strong. And the idea is that you fix F, and you just let the system evolve. And because of the quantum fluctuations, the system will switch between states. In this case, we fix F just below the center of the B stability. Here we fix it at the center, and here we fix it at a slightly greater power. So here, basically, I'm biasing the system in the lower state, so let's say the left side of my double well. In this case, I'm biasing the system on the high density side of the well. And in this case, you have two equally probable states that are switching in a certain time scale. And what we analyze is the residence time of the system in these two states, tau down and tau up. Okay? So these are the histograms of these two residence times. So just by performing a long trajectory, we build histograms of how long the system spends in one of these states or the other. In this case, you see that they follow a very nice exponential distribution, so you can think of this as a two-state system. And so we look at the average residence time, which is just basically the 1/e point. And here we plot the average residence time, and they are in agreement with the prediction for the tunneling time for B stability for this value of the nonlinearity, which is what we measured experimentally. If you like more details, I refer you to this paper. So I would like to make a break and thank my collaborators when I was a postdoc in the group of Jacqueline Bloch and Alberto Amo. And I have a very nice collaboration with Cristiano Ciuti and his former postdoc, Wim Castells, and PhD student with Jacqueline, Nicolás Carlon. Okay, so how much time do I have? 20 minutes, okay, I went very fast. So if there are, I should have said that if there are, maybe I was going too fast. If there are questions, please interrupt me, and if not, of course, at the end, I'll be happy to take more questions.
I'll make one then.
Yeah.
In the last couple of years, there has been discussion started with a paper by David Snook on the value of the nonlinearity.
Yes.
And with people reporting values which differ by 2 orders of magnitude.
Yes.
Your results seem to be exponentially dependent
yes.
on the nonlinearity. Can you use your results to settle and who is right?
Absolutely. Absolutely. Okay. This is a very nice and extended discussion, because actually there has been values in the literature that span not 2 but 4 orders of magnitude in the interaction constant. The most extreme being the one from David Snook that you mentioned, that they claim that they are in the strongly interacting limit by a lot. So if this was true, people would have seen Blockade a long time ago, and nobody has. So, okay, I don't know if he continues to claim this result or not. There is another another group that has been claiming values of the interaction constant of sort of 1 micro eV per micrometer squared. So we are somewhere in between these 2 claims. So in our case, we're still in the weakly interacting limit. And actually, we arrived to this number in 2 different ways. One is precisely through this timescale that dynamic hysteresis gives us. So if you change the interaction constant by factor of 2 from where we are, this timescale grows exponentially. So we have a very sensitive way to actually determine this interaction constant. And we also did experiments with coupled cavities where we quantify the densities, and with the interaction constant got from here, and we get a nice agreement over 3 different works. So I think there could be a factor of 3 or so off from where we are, but not an order of magnitude. So this is our view, but okay, I have to tell you, to be fair, that there are other views. Okay, so I've told you how fantastic this Polariton system is, hopefully, without trying to advertise so much. Now I'm going to try to tell you the limitations, right? And how we are trying to overcome these limitations. So gallium arsenide and indium gallium arsenide cavities are very nice because you can have this strong nonlinearity. People have been working on them for 20 years, and the quantum regime has been elusive. And there is one this comes to the nature of the interaction constant for the bare excitons, right? And recently we have seen a lot of very exciting developments, also discussed here on 2D materials and in other kinds of materials, where you can have reduced dielectric screening and also enhanced many-body interactions. But then the question is, how do you integrate these materials with cavities, right? So I started my group working in this open access tunable microcavities in collaboration with the group of Jason Smith and also Aurélien Trichet at the University of Oxford. And so the system is very nice because you can spatially and spectrally match any nanoscale emitter to any cavity mode in situ within a few minutes. So you have a flat DBR. This is just a mirror that we can coat with any material on top. And then you have a mirror over here that is, with a focused ion beam, a structure in the shape of a concave feature. And then we coat this with a multi-layer to get high reflectivity. And all of this is mounted on piezoelectric actuators. So we can just coat the flat mirror with any material, bring it into the cavity mode with the piezos, and then close the cavity. Okay? You can fix the material and change the cavity very easily within seconds, or you can do the vice versa. You can fix the cavity and change the material. Another nice feature is that by tuning the cavity length, we can change the mode volume, and we can also change the exciton fraction, right? Just by detuning the exciton from the photon, and in this way change with the square of that fraction the nonlinearity. Another nice feature is that we can have time-dependent cavities because this is all mounted on piezo, so we can just modulate, say, over kilohertz frequencies very easily. And I just show you that this system displays dynamics in this time scale, right? So you can go towards non-adiabatic dynamics with the system, also non-Markovian. So I'm going to show you first a planar cavity length scan. So basically, I'm just going to take 2 mirrors mounted on the piezos, and I'm going to scan the cavity length, and I'm going to measure a spectrum, which is shown here. And what I show you in color is the transmitted intensity. Okay? So I show you on the left the reflectivity of our DBR mirror. This is just the planar mirror. And what you see here is the stop band of the mirror. So this is basically the energy range where this works as a mirror. And then I measure the intensity as we sweep the cavity length. And you see all the different longitudinal mode numbers which correspond to this equation, right? So this is 10 half wavelengths in the cavity, 9 half wavelengths, and so on. So this is just measurement of white light transmission. Now, if you go to one of these concave features, you no longer have the longitudinal modes, but you also have the transverse modes, right? So in this case, I show you again the transmission spectrum as a function of the cavity length. And you see that as each one of these lines shows you a family of transverse modes associated with a certain longitudinal mode number. So in this case, these are the modes that we are seeing, almost 10 or so. So you can really get access to all this fine structure of the cavity modes. We can not only send white light transmission, but also do resonant excitation. So just by sending laser of a fixed wavelength into the cavity and modulate the cavity length in time. So in this case, I show you in orange is the mirror position, which is just the position of one of these pieces. In blue is the transmission of the cavity as a function of time. And so you see here a small family of transverse modes associated with a certain longitudinal mode number. This is a movie in a camera as we scan the cavity length, and you see the different modes coming up as a function of time. And this is some images of these modes, right? So recently, we are still calibrating the system. We are building the system gradually. So we took a system that we know very well, just organic molecules, where people have seen a strong coupling routinely. So we put this perylene molecule inside the cavity, and then we scan the cavity length and measure the white light transmission. The black lines here are the different longitudinal mode numbers, and you see this bending of this Polariton band, and then you see that this big region where there is no mode, and it's just because of this huge splitting because of the absorption of the molecules. We have also been looking at how the placing different materials. In this case, we put perovskite quantum cubes. So these are small cubes, about 8 nanometers in height, and they form a kind of monolayer on top of our mirrors. And again, we scan the cavity length. And you start to see, in this case, I'm showing you photoluminescence, no longer white light transmission. And you see that at the energy of the perovskite emission, which is indicated by this line, you see that the cavity emission gets decreased and then increases again. So we're not yet in the strong coupling regime, but it's going in that direction. What we want to do in the near future is to actually incorporate 2D materials into the cavity. This is just one example of a material that we have been working with in collaboration with the group of Eric Garnett and Bibla Patra. So they make this by colloidal synthesis. This is a 2D material that has a really large binding energy. You can see that this layer has something like 15% absorption in a substrate. And so we want to study this in the near future. And I think one of the nice things of these 2D perovskites is that people have recently reported that they can have enhanced many-body interactions associated with the anisotropy in the system. And the other system that we're currently building is we want to do what I just told you for the first time in a closed cycle cryostat. And so here the main challenge is stability, right? So we get all this versatility and flexibility of the system, but the price we pay is, of course, mechanical stability. And so we are working on building this system. This is a new cryostat. We're getting a kind of beta version from Montana, where the stage is mechanically decoupled from the environment, so that basically the stage is floating. And we can have these 2 stacks of piezos, not very clear here, that are supporting the 2 mirrors, and we can just tune the cavity length at 4 Kelvin, and meanwhile measure transmission through the objectives and do imaging, or also measure conductivity in this cryostat. Yeah?
What is the advantage of this material with respect to the transition metal decalcogenide that has a very high characteristic?
Yeah. So to be honest, as far as I know, so the question is, what is the advantage of this material compared to the TMDs? As far as I know, nobody has done nonlinearities with perovskites. There is not a single report that I have seen. These materials came up like 3 years ago, more or less. And there are some predictions that came up this year that show that due to the different lattice of this material and the anisotropy of the lattice, the excitons are no longer 2D, but they are kind of quasi-1D. Yeah? And so this leads to higher binding energies and also enhanced interactions. So that's, but the TMD materials are also very interesting, and we would perhaps in the near future be interesting to explore and look at the different options with these materials.
Do you plan to actively stabilize the cavity length?
Yes. So yes, the plan is to actively stabilize the cavity length. We are starting to work on this. What we are planning to do is something that is known as a pound driver Hall technique, where basically with a piezo we make an optical measurement and we have a feedback system and then a piezo actuated control system to actively stabilize the cavity length. So this is needed when we want to have, say, a fixed laser frequency and a fixed cavity length. But there are also other measurements where we want to vary the cavity length, as I showed you a moment ago. And in this case, it's actually what the approach to overcome the mechanical fluctuations is just to measure in a very fast time scale. Because the mechanical fluctuations are slow, typically not faster than a few hundred hertz. So if we can measure in a kilohertz, we will just not see these fluctuations and we'll just be able to measure narrow line widths. Okay, so what do we want to do? 10 minutes still. Okay, wow, good. So what do we want to do with this system, right? I told you now about the capabilities, and now I would like to tell you about the physics. What do we want to do with it? So I'm going to tell you one thing we would like to do is basically build an easing simulator using photons in cavities, as shown as here. So as I told you before, the idea comes from the fact that in the center of the stability you have two equally probable steady states that map to a spin up and spin down. And so this is just an illustration of a measurement of the transmitted intensity as a function of time of a bistable cavity influenced by fluctuations. In the framework of the easy model, fluctuations basically are given by temperature. Yeah? So here in this case, they're given by the detuning and the nonlinearity, which determine the number of photons in the vistability, which in turn determines how sensitive the system is to fluctuations. So there was this nice paper from Phosphike where they did the full mapping between an array of bistable cavities to an easing model. In this case, the spin degree of freedom gets mapped to the field that takes two different values. So the mean field theory for the bistable cavities is just the nonlinear Schrodinger equation that I've shown you before. And of course, for the easing model, you deal with this Landau free energy, which has, as you can see from these squared and fourth power terms, you get a double well potential, which gets mapped to the vistability. So the control parameters for us are the losses, the intensity, and of course also the driving frequency, whereas in the easing model, the distance to the critical point is determined by the temperature, and there is also the other control parameter, which is the applied magnetic field. The important point is, of course, the easing Hamiltonian, which determines the hopping between cavities. And in this case, we control this by the field overlap between the two cavities. So this is the illustration, and this is actually the first samples done by the group in Oxford, where they of lattices, where they look at, in this case, they created a 1D lattice just with a focused ion beam milling different concave features. And by changing the size and the separation of these features, you can change the coupling, which is the easing Hamiltonian. This is a 1D system, and this is a 2D system. Should I say what you're looking at is a scanning electron micrograph image of this glass substrate before we coat it with the multi-layer that gives the high reflectivity. So I told you in the beginning, motivating my talk, that was why people have been looking at analog simulators. So I would like to finish with giving you perspectives of these two reasons for our system. So one of the things that has motivated a lot of this work with analog simulators is to understand, for instance, phase transitions in the early universe or in condensed matter systems. So I'm going to briefly remind you about the phase transitions that the easing ferromagnet displays. So at low temperature, the system is in a paramagnetic state where there is no net magnetization. And as you cool it, there will be a spontaneous symmetry breaking, and the system will go either in spin up or spin down. And then this will lead to a ferromagnet state. Now, the point is that the spins only perfectly align if the decrease in temperature is infinitely slow. If you cool it too fast, meaning you do a kind of quench, then what happens is that locally, because of the critical slowing down, the system cannot follow the control parameter, in this case the temperature, right? So then the choice involved in symmetry breaking is determined locally by fluctuations rather than globally, right? So then you see that there are domains, and these domains are what are known as topological defects. And so these topological defects are very interesting because if you want to do a kind of adiabatic quantum computation, if you want to do any adiabatic protocol, they tell you about the errors in computation. They tell you how far you are from adiabaticity, right? The density of defects. And in fact, this is density of defects, understanding how the density of defects scales with the transition speed is what motivated a lot of the work by Kibel and Surek already several decades ago. And the point was that before I applied this framework to study just a zero-dimensional object, but all of the interesting physics is absent, right? The interesting physics being these strong correlations between the sides that emerge depending on the speed. So there was this paper somewhat recently in Science where people studied the Bcc Phase Transition, and they basically quenched the system. And when you go fast, you see that there are all these domains that have different small size, but when you go slow, you see these large domains, right? So this is the essence of the Kibel-Surek mechanism. The slower you go, the bigger the domains, right? So people studied this, Kibel studied this in the context of the cosmological phase transitions in the early universe, and then it was Surek who realized that we could actually learn about what happened in this early universe by doing experiments with condensed matter systems in the lab. The second topic that I would like to talk about, application, is very much inspired by work from the group of Yamamoto and recently also Natalia Berloff and Pavlos Lagoudakis that have been looking at how we can use, how we can simulate spin models to solve hard problems. In this case, hard in the theory of computational complexity is defined, I am referring to the so-called NP hard problems. So in the theory of computational complexity, there are a class of problems known as NP, which means non-deterministic polynomial. So these are kind of yes-no problems, decisions, in which every instance can be verified in polynomial time, right? So in polynomial time that scales, say, with the number of spins. So a problem is said to be NP hard when it is at least as hard as the hardest problem in NP. A very famous problem in this case is the traveling salesman problem, where you ask a salesman to go around many cities, and then you ask, is there a shortest path than the one I draw, yes or no, right? The more interesting class of problems are the so-called NP-complete problems, in which basically means that every other problem in NP can be transformed into it in polynomial time. So this is a kind of universality criterion. And it was a classic result from the 80s by this paper, which is extremely important in the theory of computational complexity, that the Ising model with the 2D Ising model with fields is NP complete. So if you're able to solve this problem, you can find the solution to any other NP hard problems with a polynomial time reduction. And so this result has motivated a lot of very interesting developments in many fields to find systems, so-called simulators, where you can realize your Ising Hamiltonian, find the ground state energy of the Hamiltonian, and this ground state energy is basically the solution to the problem that you are looking for. And the problem is basically defined by the interactions, which are the couplings and the fields and so on. Okay, so this is the perspective, and I'm going to stop here and leave more time for questions. This is a picture of our institute, and I also like to thank, who I acknowledge and thank for funding. And I also like to thank, as a postdoc, the work I did was as a Marie Curie Fellow, and recently I would also like to thank funding from the National Science Organization in the Netherlands. And thank you very much, and I'll be happy to take your questions.